Hi, my name is Grant Cotherman, and I am joined today by my wonderful teammate Scott Ostrander, SruthaKeerthi, Mylavarapu, and Shivanjali Singh. This is our final presentation for MSIS 5633 Predictive Analytics, and we are very excited to present, so let's get started. First up, our agenda for today follows the CRISP-DM data mining methodology, so we will have a quick overview followed by sections on business understanding, data preparation, modeling, testing and evaluation, deployment, and finally a conclusion. So here's our overview. Using KNIME and crash data, we'll follow the CRISP-DM data mining methodology to uncover the factors that tend to lead to crashes with severe injuries compared to those that don't. Moreover, we will build various prediction models to make predictions on injury severity. So why are we doing this? Why is it important? Well, this information could help automakers see weak spots in their designs and inspire innovation to make changes. It could also help empower engineers to help find trends in roadway issues and help them design better roads. It could also help consumers become more aware of the risks they should watch out for and mitigate. Finally, one of the more interesting possibilities would be integrating machine learning models, like the ones we're building, into navigation apps to calculate risk scores to help people make smart driving decisions. For example, a navigation app can take factors such as weather, time, car being used, and route to calculate risk scores that can advise drivers on whether or not they should be going out. Anyway, the point is there are many helpful ways this information can be used, and with that, I will pass it over to Scott to discuss data understanding and data preparation.
Thank you, Grant. The raw data we were given consists of 4 independent data files, each consisting of a different number of columns and rows. The first task was to understand the data was to merge it into one complete data set. This was done in KNIME with joiner nodes, first using a middle join for accident and vehicle, then left inner joins to add person and distract. This resulted in a complete data set containing 126,713 rows with 197 numeric values and 5 nominal values. Information contained in this data set includes information on the weather, on driver factors, on car details, as well as injury and road information. There's also information in this complete data set that we don't need or may choose to exclude. This includes pedestrian and large truck data, motorcycle data, some redundancy. For example, alcohol is contained in different forms in a few of the different initial data sets, and there are also a few variables in the data set that are not fully independent of our dependent variable, injury severity. We need to fully understand the dependent variable, injury severity. We need to understand what patterns we're going to ask the models to look for, and ask the question, how should we treat this variable to maximize our results? This distribution of values in the injury severity variable shows that the no injury value is by far the dominant value in the set. Values 1 through 4 are the values that we're going to look closely at because they include the minor and severe or fatal injuries. And then values 5 through 9 are considered outliers or unknowns, and we will probably exclude those from our final data. Starting the data preparation part of the project, the first thing we looked at was missing values. We decided to use 2 different strategies for handling numerical and categorical missing values. For numerical values, we used a missing value node to replace the missing values with a median. And we decided for categorical values we could ignore missing values since we were not going to use any categorical variables in our final data. Moving on to preparing the dependent variable, injury severity, we removed the no injury option since it would severely dominate the data and potentially skew the results towards low injury. We also filtered out values 5 through 9 that were considered outliers or were unknown values. That left us with values 1 through 4, which we then binned into low injury and high injury. Values 1 and 2 were binned into low injury, which were possible injury and suspected minor injury, while values 3 and 4 were binned into high injury, which were suspected major injury and fatalities. After this initial filtering and binning, that left us with only 29.3% of our original data. We decided to derive one variable during the data preparation process. The variable vehicle age was derived from model year using a math formula node with the formula that is shown here. We also selected 30 additional variables that potentially would help determine the severity of injury in an accident. Those included some driver factors such as age, sex, and alcohol, some environmental factors such as weather, light conditions, and surface conditions, and some accident factors such as the manner of collision, how badly the vehicle was deformed, and the travel speed at the time of the accident. After we had our variables chosen, we looked at data filtering. We decided on a minimal amount of filtering to leave as much information in the set for the models as possible. Body type was filtered using a row filter node shown here to include only values 1 through 49. That eliminated motorcycles, ATVs, and heavy and commercial vehicles from our data set. We also had to filter model year to the values from 1900 to 2021 to eliminate the 9999 values that were entered when the data was unknown in the data set. We then moved on to binning. We decided to bin 15 of our 31 total variables. Binning is a process used to transform the continuous numerical values into categorical values by separating the values into bins. The example seen here is for our binning of driver distract, where we created a number of bins that broke the data into categories that could be easily used by the models. Binning eliminates noise in the data and helps the models easily identify outliers. This all helps create better accuracy in machine learning. Seen here are the 15 variables that we decided to bin. We used both over and undersampling to balance the dependent variable depending on which model we were building. We found that oversampling worked best in conjunction with a simple 70-30 partition for most of our models. However, for logistic regression, undersampling in conjunction with a 10-fold cross-validation produced better results. For oversampling, we use SMOTE, which uses a nearest neighbor algorithm to create artificial values in the minority class, and equal size sampling is an undersampling technique that removes rows from the input data so that the values in the categorical column, in this case injury severity, are equally distributed. Some final data preparation was necessary for neural networks and logistic regression, as they are unable to use nominal values. First, one-to-many to convert nominal data to numerical data, then normalizing was used to convert the values in the columns to a 0-to-1 scale that ensures each variable has equal maximum and minimum possible values. This prevents the data from being dominated by a variable that includes very large values. Now my teammate Shivanjali will discuss the modeling process.
Thank you, Scott. For modeling, we have used decision tree model, Naive-Bayes model, random forest model, ANN model, and logistic regression. Starting with decision tree, decision tree are some of the most popular classification models due to its simplicity. We have sampled the data and used SMOTE node as it helps to oversample the minority class and provides balanced sampling. To the right, you can see 3 layers of decision tree split. Accuracy for this model is 75.7%. Talking about Naive-Bayes model, we can see the implementation model on the right. Naive-Bayes model assumes variable importance and is based on Bayes' theorem. We have used SMOTE node in this modeling as well. This model uses a default probability of 0.0001 and a standard deviation of 0.0001. Accuracy for this model, according to our modeling technique, is 76.6%. Moving on to the random forest model. We have used SMOTE node here as well, so as to oversample classes, minority classes, and provide balanced sampling. Random forest model uses 100 trees and are an assembled model of decision tree. Accuracy for this model was 83.7%. This is the variable importance graph. Random forest learner was used to derive a variable importance graph that is displayed here. What we worked on is ANN model. Here we have used MLP model, which is a specific type of ANN. It is mostly useful for classification problems. Here, neural network requires numeric data, so one-to-many node and normalizer node has been used. We have used smooth node here as well. You can see the model on the right. Accuracy for this model was 75.2%. Moving on to our last model, that is logistic regression. In this model, we have used X aggregator node to combine data from multiple input streams. Here we require the same conversions as ANN, so it is derived from the same converter node. Accuracy for this model is 72.4%. Moving on for testing and development to Keerthi. Thank you.
Thanks, Shivanjali. The next phase is evaluation. Model evaluation was carried out to assess the performance of the predictive models used in the study. Our study has identified key factors that significantly influence high injury severity in road accidents. The area under the ROC curve was used as a graphical measure of the model's effectiveness. So here you can see 5 different models ROC curves were analyzed, with random forest having the highest area under the curve and decision tree having the lowest. We have combined all the ROC curves to provide a comprehensive view of the model's performance. This slide presents the results of our evaluation of 5 different models for their ability to rank factors that affect injury severity. The random forest model performed the best overall with the highest area under the ROC curve and also the accuracy. The table provides additional information on the combined ROC curve values, accuracy, sensitivity, and specificity for each of the models. These metrics can help us understand the performance of each model and make informed decisions about which one is best suited to our needs. Here we have also mentioned the ranking according to the accuracy. Next phase is deployment. The factors with the most significant impact on injury severity were identified as ejection and alcohol levels and the type of restraint system used. Here are some proposed deployment measures which include implementing social awareness programs, increasing penalties for individuals who do not use restraint system, and also the prioritizing the focus on the second tier factors that influence injury severity. So some of the deployment steps are obtain funding and resources, which is securing necessary funding and resources for the program's successful deployment. Next is partner with roadway safety organizations to raise awareness, like establishing partnerships with national road safety organizations to develop effective public initiatives and incorporate up-to-date data into predictive models to improve their accuracy. And in order to further reduce the risk of harm and promote road safety, it is definitely important to focus on improving safety measures based on tier 2 factors that influence injury severity. In conclusion, to sum up, we cleaned the data using binning and removed information that would skew our findings. We utilized the 5 different models, which are the decision tree, random forest, linear regression, naive Bayes, and multi-layer perceptron, and found that the random forest achieved the best score on the ROC curve at 0.813. We believe that utilizing these models on a regular basis can continue to provide insight and actionable intelligence to business, governments, and consumers. Thank you for taking the time to listen to our presentation on the project we completed. We appreciate the opportunity to share our work with you today. Our special thanks to Dr. Delan for teaching us the 5633 course and for guiding through this project. And also, finally, don't forget to buckle up. Thank you.